Welcome back to our second video. I want to take a moment just to explain what this video series is going to be about. I've been looking for a way to help my students at home when they are, well, on their own to do the assignments, or if their parents need some help. You know, some of this is material we haven't seen since we ourselves were in elementary school, so I wanted to give you the opportunity to get kind of a refresher. It also will help the kids out in case, well, you know, we forget what was talked about during the day and what we practiced during the day. So this second video actually is to carry on from the first one about greatest common factor. In video one, we talked about using a T-chart in order to find the factors of a number and then find the greatest common factor between two numbers. In this video, I'm going to talk about prime factorization, which is a second method for finding the greatest common factor. Now, to talk about prime factorization, we do have to define a couple terms. And so I've just put them up here, and if you need to freeze or pause, you may do that. But our first term is, what is a prime number? Well, and a prime number is a number that has factors that come only from 1 times that number. Now, we call that the identity property. And in the end, a prime number will have only 2 factors, 1 and itself. So, for example, 7, the only numbers that will multiply into 7, in other words, factors, are 1 and 7. 1 times 7 is 7. 2 won't multiply into 7, 3 won't, 4 won't, etc. 7's prime. Composite numbers, on the other hand, as you'll see on the bottom, there are numbers that have 3 or more factors. And we say 3 because of those special numbers like 4, where you have 1 times 4, and then 2 times 2, and really when we have 2 times 2, that's considered 1 factor 2. So 3 or more factors, it's a composite number. 2, it's a prime number. And we need to know that in order to do prime factorization, because the idea behind prime factorization is to create a tree, or as I call it with the kids, a grapevine, that will break the larger numbers down into their prime factors, or simply put, numbers that that are prime, and then when you multiply them back together, they will get you back to your original number. So, for example, 12. When you take the number 12 and you break it down into its factors, you can start with the multiplication problem 2 times 6. Now, if 12 is a prime number, for example, well, prime isn't, or excuse me, 12 isn't, but if you have a number like 7 where it's already prime, you can't break it down any further, and it's already been reduced to its prime number. But 12 is a composite number. 12 is made up of factors like 2 and 6 and 3 and 4. And you can choose either. You can do 3 times 4 or 2 times 6. It won't matter. You'll come up with the same prime factors. In this case, I chose 2 and 6. 2 times 6 gives me 12, and as you can see, I show 2 as one branch and 6 as the other branch. And then I look at my numbers, and you'll notice I circled the 2 because 2 is, of course, a prime number, which is why I sort of like the idea of having the kids think of it like a grapevine, that it's falling, and then as we hit those grapes, we circle them, the grapes, of course, being the prime numbers. 6 is not a prime number, it's composite. 1 times 6 will give me 6, but so will 2 times 3. So you will see I split the 6 down, and it becomes 2 and 3. 2 is a prime number, and 3 is a prime number. So we circle 2 and 3. To display that, then, we ask the students to rewrite a new multiplication problem showing those prime numbers. So we take the 2 times 2 times 3. And you can always check these by multiplying them back together, and you should come out to your original multiple of 12. 2 times 2 is 4. 4 times 3 is 12. We write it as a new problem. 2 times 2 times 3. Now, because we're in 5th grade, we also are starting to use exponents, and an exponent is a way of showing multiple numbers, or I should say rather, when I have the same number being multiplied many times, it's a way of showing that. Since 2 is here 2 times, I would say 2 to the 2nd power times 3. And in the end, my prime factorization for the number 12 would look like this. 2 to the 2nd power times 3. At this time, I'll pause, because what we're going to do next is we're going to look at how we can use prime factorization to find the greatest common factors of two numbers. And welcome back. I realize for you it was not a pause. For me it was. I would like you right now on a sheet of paper to write the numbers 12 and 18, because 12 and 18, if they look familiar and you watch the first video, they are the same numbers I started with in the other video. What we're looking at is, can we come up with the same common factors and greatest common factor, really is what we're looking for 12 and 18 using prime factorization as we did using the T-chart method. What I'd like you to do right now is, much like I just did on the number 12 earlier, I'd like you to find two factors for 12 and two factors for 18 that when they're multiplied together will give you 12 and 18. And in a moment, we'll come back. Now, I will tell you, yours may not be the same as mine, and that's okay. We'll be back in a moment. Please pause. All right, welcome back again. Did you find two factors for each of them? Now, I do want to point out mine may not be the same as yours, and that is okay. For 12, I decided to go with 3 times 4, and with 18, I decided to go with 3 times 6. Now, for 12, you may have chosen 2 times 6, and for 18, you may have chosen 2 times 9. And that's okay, because in the end, we should still end up with the same prime factors. Now, looking at yours, if either of yours are like mine, right away we notice there's a 3, and 3 is a prime number. 3 cannot be multiplied by any other factors other than 1 and 3. That's the only way to get that product of 3. Therefore, they're prime. Well, and as I showed you earlier, we're going to circle them. So on my paper right now, I am going to circle my 3's. 4 and 6, on the other hand, are not prime. They are composite numbers. And therefore, I can find more factors for them. Now, if you went with 2 times 6 and 2 times 9, you circle your 2's. But you still have a 6 and a 9 left, and they're both composite, and there are multiplication problems, factors, that can be used to find those products. So let's take a moment and we'll split up our 4 and 6, or your 6 and 9. All right, how did that go for you? For me, I ended up with 2 times 2 to give me my 4, and I end up with 2 times 3 to get me my 6. Now, if you did the other numbers, if you did for the 12, 2 times 6, yours now has a 2, or excuse me, I'm on the wrong side. I now have a 2, you would have, excuse me, a 2, and probably a 3. But regardless, notice we do have the same numbers. And if you multiply them back together, you should end up with 12 and 18. 3 times 2 is 6, 6 times 2 is 12. 3 times 2 is 6, 6 times 3 is 18. Our next step is to rewrite these as a multiplication problem. Please do that right now while I do mine. So for my 12, I have 2's and 3's, and I really like things in order, so I'm not going to just throw my numbers down in any old order. I usually start with the smallest numbers and work my way to the larger numbers. So instead of saying 2 times 3 times 2, I'm going to write 2 times 2 times 3. And for my 18, I see I have a 2, but 2 3's. So again, in order, I'm going to start with my 2 and go 2 times 3 times 3, which will end up giving you a problem like this. Pause if you need to. All right, the next step then is we do need to show these in exponents. So I have, for my number 12, I have 2 2's, 2 times 2. To show that, I will use a base number 2 with the exponent 2. We would say that is 2 to the second power, or 2 squared, times 3. So for your 12, it should now look like this. 2 to the second power, meaning I'm multiplying 2 times 2. I'm multiplying the number 2, the base number, by itself as many times as the exponent tells me, in this case, 2. For the 18, I have 1 2, but I have 2 3's. So I'll write 2 times 3 to the second power. And it should look like this. Now is when the fun begins, because now we have the two numbers and we do have their broken down prime factors. In order to find the greatest common factor using these numbers and this method, what we're going to do next is use the definition again of greatest common factor. And the key to it is that middle word, common. What we are going to do now to find the greatest common factor is we are going to pick from the list. I find it easiest to use this first multiplication problem, but you can use the exponential problem as well. But what we're going to look for are any numbers that these have in common. Any number they have in common, you get to use for finding the greatest common factor. So for example, 12 has 1, 2. So does 18. So one of the numbers they have in common is 2. So I would write that down. What I'm going to do is at the bottom, I'm going to put a GCF, which is short for greatest common factor. Because one of the numbers they have in common is a 2, I'm going to write a 2 down. Now notice I didn't get 2 2s. If they have it in common, I get one of them. Any other numbers they have in common will be multiplied to this number. So we look at it, and are there any other numbers? Pause for a moment if you need to and look. And hopefully you discovered why. Yes, there is. They have a 3 in common. Both 12 and 18 had a prime factor of 3. I get 1 3 because of that. And I would write that 3 down at the bottom as a multiplication problem. And my greatest common factor would be the product of the numbers that it had in common. It had 2 in common, and it had 3 in common. All the other numbers are left out. We'll get to those when we do least common multiples. But for right now, these are just the numbers I need. A 2 that they had in common, and a 3. 2 times 3, of course, is 6. And that gives me my greatest common factor of 6. Now, if you think back and you remember, we looked at a division problem in the last video where we said you can now take that greatest common factor, and if this was a fraction, 12/18, this is the number I would divide by to get simplest form, which would have been, I believe we said, 2/3. Well, hopefully that explains a little better how we are doing 2 different methods for greatest common factors. If you did not watch the first video, I recommend you do. That showed how to find the greatest common factor using our charting method. I call it the T method because essentially we're making a T. And hopefully these 2 methods will work for you. If you have questions after this, when you come to class tomorrow, please make sure to bring your paper with you and we will go over them together. Have a good evening. Thank you very much. A little postscript here, but something that didn't come up earlier in the video. What happens when the 2 numbers do not have a common factor other than 1? Well, that means one of 2 things happen. Either one of the numbers or both of the numbers were prime, and therefore the only numbers they could have in common were 1. Unless, of course, the prime number actually will be a factor of the larger number. But chances are if all you saw was 1, it's a good chance they were prime numbers. The other chance is that there are numbers that simply do not share common factors. And if that's the case, then we don't have a greatest common factor. The greatest common factor is 1, which is, as I've told the kids, not the most useful thing, because if I have to simplify a fraction, dividing by 1 won't change the fraction at all. The number is already in simplest form, which isn't a bad thing. That means there's not a lot of extra work that has to be done. I just wanted to add that thought before we moved on here. So have a good evening, and we'll see you in the next video.